Okay, gang, this video's been crazy. QuickTime has crashed more times than I even want to get into because I'm afraid I'll start using foul language. But anyway, as you noticed, the second video it ended abruptly. So unfortunately, I didn't even know it had ended, and I went ahead and was just talking my little heart away and completed the lecture. So let me go ahead and complete things. I've already got things written out, and so this should go pretty quickly. At the end of the previous video, I had created the variance-covariance matrix, which you see there, and we were examining the standard error for B1, which is where the second row and second column intersect, and I took the square root of 9.09 to get 3.015, and I got calculated the Bonferroni T critical value to be 2.67. What I did next was I left R, hopefully, and I showed that our 95% confidence interval for beta 1 is, let me get back in here, okay, negative 3.74 to 12.40. So I'll show the calculations there. Notice this contains 0. Which makes sense because we failed to reject. If we look back at the coefficient output for our model, we failed to reject the null. Our p-value is greater than 0.05, which confirms the output earlier. The next thing I did is got into the estimation of mean response. And this is not to be confused with what we just did, estimating a coefficient. This is estimating a mean response for a fixed level. But since we have multiple levels in this illustration, we are fixing multiple levels. So we're looking at the mean response, or the expected value, holding all the levels constant at a particular value. So let's say that a nutritionist would like to estimate the expected or mean body fat for women, again 25 to 34 years old, with tricep equal 25, thigh equal 52, and a mid-arm of 28. So guys, what we're doing here is I'm yawning here. We're focusing on the mean response just for this particular profile of women. First thing I want to do is get a little bit of notation. Anytime I use the notation sub h, I'm looking for a predicted mean response at a level that's held constant. So xh sub 1 will be my level that I'm holding constant for the first predictor, xh sub 2, the level I'm holding constant for the second, and so on and so forth. Guys, ultimately I put all this together to create my design matrix for this, but we don't call it x, we call it x sub h. And notice that the 1 that we include there is for the intercept, just like the row of 1s for our design matrix. To create our point estimate, we call that y hat sub h, again consistent with the h. And we make the calculation by taking the transpose of x sub h times beta. Now I want to do that, and I did it, and I'll take you over to R and show you the calculations there. So guys, what I did first of all is I wanted to create the x sub h matrix, and this is the way I did that. I used the C command to kind of bind the numbers in the matrix. So you guys are old pros now at creating matrices in R, so that should be pretty clear. And the next thing I did is I created the predicted y sub h, and I called that, PREDYH. And those calculations should be pretty clear. And then I just called up the value. Okay, so my predicted body fat for a woman of this profile, again, that's this specific tricep, specific level measurement of thigh, and so on and so forth, is 15.67. Okay, but guys, this is just an estimate. And we should know by now that if we have just an estimate to generalize to the population, we need a confidence interval. Guys, I'm going to use the same Bonferroni T but the calculation for the standard error is a little bit different. So the standard error squared, we take the x sub h transpose times the variance covariance matrix times x sub h. And notice below each of those I've given you the size. So we have a 1 by 4, a 4 by 4, and a 4 by 1, which clearly says we're going to get a 1 by 1. So if we take the square root of that, we're going to get the standard error for the predicted value for the body fat of this particular profile of woman. So guys, I used R to make those calculations, which I'll show you right now. So guys, the first thing I did, let's think about that. I took the transpose of XH times the variance covariance. I created the variance covariance matrix way back here. And I get a 1 by 1, which is 13.7451. I take the square root of that to get the standard error. Okay? So gang, at the end of the day, what I did is I put all the numbers together. So I have a 3.707 standard error. The T critical is 2.675, again from the Bonferroni estimate procedure. So guys, at the end of the day, our 95% confidence interval for the predicted or expected body fat for the profile, woman 25 to 34, tricep 25, thigh 52, mid-arm 28, will be 5.75 to 25.59. So quite a bit of variation there, but you know, we're using kind of a small sample size, only 20 women. So guys, that's all I got. This is the only video. No, this will be the third video. Next week we'll start what we call the extra sum of squares. Where does all that come from? What does it tell us? What does it mean? How does it help us in learning more about regression models? So guys, hopefully QuickTime doesn't crash before I get this thing uploaded. So have a good one. Take care.